another day, another lecture. So I hope everyone is a little bit in the mood already to dive deeper. Okay, so our calculations are starting. The calculation parts of our lectures are starting. So we need a little bit more focus time and motivation to really study as we approach the end of the semester. Okay, at if I'm not mistaken, the final week, week 7 kasi is the week of December 9 to 4 to 15. And same as during the midterms, uh, fluid mechanics is one of the subjects that will have its exam on the first few days. So I'm expecting our exam to happen on December 14, that's a Saturday. And after 14 kasi, I will not be around a little bit. I have a trip abroad. So I'm hoping everything, all of our requirements can be settled by 14. Okay, I think the same as last year, the deadline of uploading will be after Christmas, but I am hoping it will be extended after New Year. So, but our goal is to finish everything with flying colors, all the discussions by December 8th. That's a Sunday. And looking at the calendar, we will have because November 30 is a holiday, so we will have one no class day on November 30th because of Bonifacio Day. So that's one day less for all of our remaining activities. So sino ngang class reps? Si Luzel ba?
Yes po, sir.
Hello po. So, ask ko lang if kasi nakikita ko may mga subjects na nagpa-plan tour. Kayo ba ay may gano'n?
Wala po, sir.
Okay, so walang expected na plan tour or trip outside until December.
Wala po.
Okay po. So, yon. So, I will try to spread out pa rin everything within the remaining days so that we won't get burnout. That there will be no burnout day naman. And maximize our face-to-face discussions for your questions or clarifications. Okay. So for today, you jump to energy of fluids topic. Okay, but before that, I just have two agenda lang today. First is a GCR, Google Classroom question number 8 for multi-stream flow. And then yung theoretical discussion on the elements of fluid energy. Okay, by the way, last week, I forgot the day. I think this week, I released a Excel that can give you the standing. By now, all of your past assessments have been released back to you except problem set number 1, which the goal is I will send back this. You will submit that to me tomorrow. The physical copy you will submit to me tomorrow, and then I will give the score back this week. I mean next week. Because I have checked the voice recordings through the PDF and voice recordings, but I want to check the problems themselves, the individual problems on the physical copy. That's why I want to collect tomorrow the physical copy. So I will check physical the answers, the problem answers there, the 10 problem answers. Your score for the problem set will be the a product of the physical answers on the problems times the score on the recording of the recordings. Yun. So, and then last week nga, I released a tool that if you put your SR code, you will see the standing. However, that is based on assumptions, assumed grades of all our remaining activities. So slowly, as we get to do each activity in the next few weeks, I will update that tool to change the assumed scores to actual scores as we go along them. Okay, so hopefully before the end of the finals, all of the assessments will be included in the calculation, and you will know your target score or target grade in the finals to get a passing grade. So last two sessions, we discussed uh, first is the concept of fluid flow, and then last week we discussed problems involving fluid flow. I think for single flow problems, it's easy to understand, easy to grasp, but for multi-stream flow, it's a little bit advanced. We have one example last week of multi-stream flow problem wherein we have one inlet and two outlets. Two inlets, they mixed and they go out to one outlet. So two inlet, one outlet. So for now, GCR number 8, multi-stream flow example or activity, seat work actually, is two outlets, one inlet, two outlets. Okay? It's a theoretical problem because in theory, it should act as, instead of a mixer, it acts as a separator, right? So I have a fluid that is entering the chamber. Then ideally, the chamber will separate the fluid into two streams that has different properties. So in reality, this is very difficult, almost impossible. But in theory, we will just want to see how to solve problems that are of this style. I think one in your problem in your quiz number 3, number 5, I think I asked you for feedbacks. And one feedback that caught me is that they want to have examples that are same level as exam questions. So this is one adjustment to that. I want to try giving you a little bit more advanced examples so that you can feel how to solve them and you will not get culture shock or exam shock when the final exam comes out. Okay, because they are relatively in the same level of difficulty. Okay, so GCR number question number 8, a magic tea that can split seawater into fresh water with an SG of 1, which will flow through the 2-inch outlet pipe and byproduct seawater on the 4-inch outlet pipe. Okay? The velocity of the two outlet streams are equal. The stream, so that's one condition. The velocity of the two outlet streams are equal. Okay? Second condition, the stream density in the 4-inch inlet pipe is 1,250 cubic meters per second. And volume flow rate, yes, 10 cubic meters per second. Density pala tong 1,250. Wait lang. So density, that is kilogram per cubic meter. Yeah. And the flow rate is 10 cubic meters per second. I want you to find the outlet velocity in meters per second and density of byproducts seawater in kilogram per cubic meter. Okay? So before we start, I would like you to show a diagram of the problem. Okay? So this question naman, I will keep this slide open, this slide. Pero but this full text question, I will upload in the Google Classroom so you can refer later. Okay, then if you notice here, we have 15 minutes to do this. Okay, so diagram, if we translate the problem into the diagram, this is the inlet. Okay, so seawater comes in here with a Q1 or volume flow rate of 10 cubic meters per second and a density of 1,250 kilograms per cubic meter. So D1 or point 1 has a diameter of 4 inches. Okay, and then the device separates the seawater into two streams. One stream is fresh water, the second stream is seawater. And the problem states that the fresh water will flow through the 2-inch outlet pipe. Okay? It means that your fresh water will come to this side, to this end. So let us label this so you will not get confused. Fresh water. Oops. Yan. So the outlet pipes are 2-inch and 4-inch. Okay. So the problem states that fresh water will come out of the 2-inch outlet. It means that the other outlet pipe, that other outlet pipe will release seawater also. Okay, but of course the density is different. Okay, because there is already a split in the fluid flow, so the properties of the two flows are different now. Okay, so ito yan. Fresh water SG equals 1. Okay, and then it also stated that the velocity of the two outlet streams are equal. So that is where V2 equals V3 here is placed here to remind you that the velocity of outlet 2 and the velocity of outlet 3 are equal. You're asked to get, so let's me copy this so you will remember. Yeah. So find the outlet velocity in meters per second and the density of byproduct seawater, meaning this one, the one coming out of T3, in kilogram per cubic meter. Okay. So you can refer to the slides last week that is already uploaded on the classroom. And remember that the key here is the conservation of mass equations. Q in equals Q out and mass flow in equals mass flow out. This is Q in volume rate, volume flow in. Volume flow rate in equals volume flow rate out. Total. Okay. So you have 15 minutes to do this sit work to test or to exercise your knowledge in multi-stream problem because in the final exam most likely one problem will be a multi-stream problem multi-stream problem. So I hope you get comfortable with solving problems like this. Okay? So you have it's 9:26. So I will have until 9:45 until this time runs out or maybe and round it up to 9:45 before we go on to the next topic and then we will discuss the solution to this tomorrow during our face to face. Okay, if you have questions, then just raise your hand. I'll just be here in the background. By the way, this GCR problem is 15 points. By 15 points, and it will have no denominator. Okay? Meaning it will be, it's like a bonus question that will be added to your bonus quiz or additional quiz. So I'm doing this because after checking everything, I think quiz 2, some of the quiz 2, some of you have not so good at scores in quiz 2. So to pull quiz 2 up, I want to use the Google Classroom questions to pull the other quizzes up. Okay, so hope you do this because ano, sayang ang points. Okay, because it'll like a bonus addition to the quiz, bonus score to the existing quiz score.
Sir, sir.
Yo.
Yang complete decimal ka po. Wala pong nakaano eh.
Ah, wala. Isa. Sige, one decimal.
Pareho na po yan, sir. Sa ano.
Pareho. Hindi,
Sige.
sige. Whole number na lang para madali ang buhay natin. Kung may value yung whole number na lang. Pag wala, sabihan niyo ako.
Sige pa. Thank you pa.
The Google Classroom is already uploaded, so you can put your answers there. One tip to get the velocity is to note that V2 equals V3. Okay? It means even if you have two flows, then the value of velocity of those two outlet flows are equal. So, which means you only have one velocity to find, and that velocity is same for both the D2 and the D3 outlets. Then after you solve that, then you move on to the density. And the only unknown density here is the density of the D3 of the byproduct seawater, because the other branch is fresh water. So you can solve for the density of that. Okay, so you only still one unknown for item number B, the density. Okay, again, for now, show your answers in whole numbers. So for the question, you will input two answers. And the key to check is, or well, not really check, but to get a feel if your answer is correct, the densities of the mixed of the mixed fluid should always be in between the density of the two separate fluids. Whether those two separate fluids are in the inlet or the outlet, the density of the fluid once they mix should always be in between the two original density values. The timer here is 0 already, but the GCR you can upload until 45, 9:45. Okay, so I think time's up. Okay, so hopefully most of you got to be able to solve that, but tomorrow we will discuss in class, in face-to-face. Okay? But for now, let's move on muna sa ating next topic, which is the energy of fluids. Okay, so remember when we started the SEM, I showed you this diagram, the different branches of fluid mechanics. First is the fluid statics. So that is your rho GH, okay, everything rho GH. So that is discussed from day one to midterms. Okay, and then I said that fluid kinematics and fluid dynamics will be discussed midterm onwards. For the past two meetings, we discussed fluid kinematics, which is the study of fluids in motion, considering geometry only. So this is your area times velocity, your density times area times velocity, and your density times gravity times area times velocity. Okay, your volume flow rate, your mass flow rate, and your weight flow rate. Okay, all of those consider geometry only and no consideration of energy plus geometry plus energy. Okay, moving forward, we are now in the last category, which is fluid dynamics, study of fluids in motion, considering geometry plus energy. Okay, so we are done. Theoretically, we are done with fluid statics and fluid kinematics. Right? But tomorrow in our face-to-face, we would still discuss problems about fluid kinematics. So more on hands-on tomorrow and sit work and group work. Just to give you more examples on fluid kinematics. But topic-wise, we're already on the last part, fluid dynamics. So we will now consider energy in our discussion of fluids in motion, at motion. Okay? So let's start with that energy. Okay? Energy in fluid is in the form of mechanical energy, which is the form that can be converted to mechanical work completely. Okay, mechanical work, it means you can use this energy to make objects move. Okay? So you can make objects translate, which means you can push or pull objects using fluid, or you can make objects rotate. Okay? So, mm, next week we will discuss more of those types of machines on how fluids can cause mechanical and can 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 convert energy to mechanical energy. But for today, we would like to focus more on the energy part. Okay, dun sa energy itself. What composes that energy of fluids? Okay. So the energy of fluids is composed of two types, the potential energy of the fluid and the kinetic energy of the fluid. Okay? The potential energy of the fluid involves the elevation energy and the pressure energy. Okay, these are potential because these energies are not because of moving particles. Okay, so elevation energy is based on elevation and pressure energy is based on the pressure. So these are properties of the fluid that does not necessarily mean they are flowing. Okay, even if the fluid is static or not moving, for example, your fluid in a tank or fluid in a glass or fluid in a container, in a pool, they possess this potential energy. Okay, because this potential energy is um, in a fluid even if they are not moving. Okay, because the potential energy. Kinetic energy naman is the energy that requires movement or motion. Okay? If an object is not in motion, then it does not have a kinetic energy content. But if an object is in motion, then it has some amount of kinetic energy. Okay? Any question po on this concept? I do not know if you discussed this in Thermo 1, but Thermo 1 kasi is more on thermal energy. Okay, creates pressure creating thermal energy. But in fluid mechanics, our pressure does not create any thermal change or change in temperature. But it can be converted into mechanical energy. Okay. Any questions po? Okay. So let's start with the potential energy part. Okay, the energy that is present in the fluid if it is in motion or even if it is not in motion. So the first element there or component is the pressure energy. So for fluids, this is the energy that is that has the ability to do work by virtue of the difference in pressure between 2 points. Okay? So it means just because of energy, you can remember mechanical energy is related to movement, to actual motion, motion of machines, motion of parts. Okay? So pressure energy can cause actually mechanical elements or mechanical parts to move because of the pressure. Okay, so papaano yan? For example, if you have a tank, okay, if you have a sealed tank and you increase the pressure inside, you can actually cause the tank to explode. And that explosion will cause failure or damage to the physical metal or physical material of the tank, and that damage is actually mechanical energy at work because you are in a way you can think that there is movement in the tank as it bursts open or as it becomes damaged. Okay, it, if you can imagine it, it's also pressure in a balloon. Okay, if you have a small plastic balloon, rubber balloon, if you blow air into it, okay, you increase the amount of air inside, you increase the force on the inside of the balloon that causes it to expand. And that expansion is actually movement already because of the pressure difference inside the balloon and outside the balloon. Okay, so the higher the pressure inside, then the more stretch or the more push or force that the pressure is exerting on the balloon, causing it to expand. So that energy is pressure due to pressure energy alone. Okay? So pressure energy, if you can remember your physics, there are equations of energy. Pressure energy is given by P times V, or pressure times volume. Okay? If you do a unit analysis or dimensional analysis, your pressure for pressure is newtons per meter squared. Your pressure per volume is meter cube. So if you multiply both units, you will get Newton times meter or Newton meter, which is equal to joules, which is a unit of energy. Okay? It means if you have a pressure within an enclosed volume, then you have a potential energy in the form of pressure energy, okay? In the form of in given by the formula pressure times volume, which has the units Newton meter or joules. Okay? Any questions? So that is the pressure energy component. So as long as you have a volume and you have a pressure, then you have a pressure energy content, a pressure energy content or value. Okay. Next naman, the kinetic energy. So the kinetic energy naman, again, it is based on the fluid's ability to do work by virtue of its velocity. Okay, so velocity. So yan yung mga ano nyo, pressure washer. Okay? Paglakas nung actually pressure washer sa car 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 wash. Okay? It's not the, well, may factor yung pressure, yes. That because the idea is the higher the pressure, the stronger the hose pressure. So the stronger the water stream. But actually, what causes the stream to become powerful is the velocity. Okay, because well, interrelated. They're interrelated. The higher the pressure, the higher the velocity. But if you but the direct reason for the strength or the power of that pressure washer is the velocity. Okay, because of the velocity of the water, you are able to get dirt from your tires or from your car or from, for example, from your garage. If you pressure wash the floor of your garage, it's actually the velocity of the fluid that is doing the work. The pressure is just a indirect source of the energy, but the direct source of energy is the velocity. The higher the velocity, the stronger the kinetic energy. And for fluids, it's the same. The faster your water stream is, the stronger the kinetic energy is. You can feel this if you go to a waterfalls. Waterfalls, if you go under the falls, okay, you can feel the force or the impact of the water above you. So the higher the falls, the stronger or the faster the velocity of the water is as it reach you. And so the stronger the push or the impact of the water is to your body. Okay, you can say it has a that the pressure or the height of the waterfall has impact, has contribution to that, but that if you think of it directly, it's the velocity of the waterfall, because of gravity. As the waterfall water falls, is it becomes faster, so it has higher velocity, and higher velocity means higher kinetic energy. Again, the equation for kinetic energy from your physics is 1 half mass times v squared, or 1 half mass times velocity squared. Okay, so it is impacted by two variables, mass and velocity. So the higher the mass or the velocity, the higher your kinetic energy is. If your fluid is falling, for example, of waterfalls, then your velocity can be solved through your acceleration due to gravity. Okay, so it will change a little bit. Okay, but for our discussions, we will not be considering gravity or acceleration due to gravity to compute for the velocity. Okay. Again, doing what's this? Doing unit or dimension analysis, our 1 half mv squared, our mass is kilogram, our velocity is meters per second. Okay, I remove the 1 half na kasi we are just analyzing the units. Units lang naman. So 1 half is a constant, so it is unitless. So mass is kilogram, velocity is meter per second, but it is squared. Then you will get kilograms times meter squared per second squared. Okay? Then take out one of the meters. Okay? Take this out, then you will left with meter per second squared times meter times kilogram. And this portion, the kilogram times meter per second squared, is your Newton. Your mass, your meters is M. Again, you get Newton meters, which is equal to joules. Okay, so it's still a form of energy. Any questions for kinetic energy? Okay. And third, and the last element of our energy of fluids is the elevation energy. So for fluids, the elevation energy is the ability to do work by virtue of the position, or to be specific, vertical position or elevation. Okay? It means it means as the fluid is placed on a higher elevation, then it gains a higher elevation energy. Okay? So again, this is based on a reference point. Okay? For example, if the ground is your reference point, if the first floor is your reference point, then as you go up the floors with respect to the first floor, then you get increased elevation energy. Okay? So it is possible also to use different elevations as reference. For example, if your reference point is the second floor, then your measurement of elevation energy will just be based on the second floor instead of the first floor. So it has a reference point, or kumbaga, it has a zero elevation reference. It's like a relative pressure, that in relative pressure, your reference pressure is the atmospheric pressure. For elevation energy, your reference elevation is a point that you specify, wherein that's your zero point. That's your zero elevation. Okay. Then from there, going up, that is your measurement of elevation energy. Okay. The formula for elevation energy, or basically potential energy due to elevation, is mgh, mass times gravity, acceleration due to gravity times height. Okay. Or some books, if you read some books, their height component is referred to as z. So some books will give you mgz, but they're the same. Mass times acceleration due to gravity times height. Okay? Doing dimensional analysis again, your mass is kilograms, your acceleration due to gravity is meters per second squared, and your height is in meters. Okay? So again, kilograms and meters per second squared, when combined, will become Newton. Then you have your meters alone. If you combine that to newtons, you will get again joules. So again, it's a measure of energy. Okay. So those are the three elements that we will consider for fluids: the pressure energy, the kinetic energy, and the elevation energy. So combining these three, we get an equation of P times V. By the way, if you notice, I put a subscript sa volume because there's also a V here for velocity. Okay, so you might get confused. So to prevent confusion, for volume, I used VOL, V sub OL as my variable. Okay, to distinguish it from V velocity. So the total energy then with these three elements is pressure times volume, PV, plus 1 half m times V squared, mass times velocity squared, plus mgz, or mass times gravity times height. So this is the total energy of a fluid. So what are the factors affecting the energy? Pressure, volume, mass, velocity, and height. Okay, so all those factors contribute to the amount of energy in a fluid system. Any questions po? Okay, so given this equation, if I give a system that has a pressure, a volume, a mass, a velocity, and the height, then you can solve or compute for the total energy content of that system. Okay? And it means that system contains this much energy. If you have the correct tools or the correct machines, then you can extract this energy from that system. Okay? So this is our, kumbaga, it's our theoretical maximum energy of a fluid system. Okay? Now this is total energy. The unit is joules. Okay? We also have specific energy, okay? Which is energy per unit kilogram, per unit mass. Okay? Joule per kilogram. The unit is joules per kilogram. Energy per unit mass. So to get this, we will just divide our original equation by mass. Okay? This equation is the total energy. To get the total energy per unit mass, then we divide each element by the mass variable. So that will be P times volume over M plus 1 half mass times velocity squared over M plus mgz over M. And we will get P, pressure, times our volume over mass is density. Volume over mass is specific density, 1 over rho. Okay, V over M, 1 over rho. So P over density, or P over rho, becomes P over rho. For the kinetic portion, 1 half mv squared divided by m, then one of the m will just cancel out. So you will be left with v squared over 2. And for the elevation energy, mgz divided by m, the m will also cancel out. You will be left with g times z. Okay? So our equation for the total specific energy becomes P over density plus V squared over 2 plus acceleration due to gravity times Z. The units of this is joules per kilogram. Any questions po? And lastly, we have another form. If the total specific energy is total energy divided by mass, we have something called energy head, okay, which is energy divided by weight. Weight, okay, your rho times g, your mass times gravity. Your mass times gravity, weight, rho g. Mg pala, sorry, mg. So this is the mass energy per unit weight. Okay? So again, if this is energy per unit weight, energy is Newton meter. Okay? Weight is newtons. Okay, newtons. So they will cancel out. What you will left is meters only. Okay, meters, or yes, meters only. But even so, take note that this is not a unit of length, meters. This is a unit of energy per unit weight, but but it becomes meters because the Newton elements cancelled out. The newtons of from the energy and the newtons from the weight. Okay, so its unit is meters, but it is a unit of energy, which is called energy head. Okay, so do not get confused moving forward. So always label your values. Okay, so not because it meters, not because something is in meters means it's the elevation. Where sometimes even if it is in meters, it is actually the energy head already. Okay, so how do we derive? So similar to how we derive the specific energy, okay? So we will use, so this is our original equation. Original equation is this one, total energy, EV 1 half mv squared mgz. Then we say that the energy head is this equation divided by weight, okay, which is given by mg. So per element, For the pressure head, that is PV, pressure volume, divided by mg, which is the weight. Then that will be equal to the V over M. V over M here becomes 1 over density. Okay? So it becomes P over rho G. Okay? And remember, rho G is this one, the specific weight. The weight, no, weight density. Weight density pala to. The newtons per cubic meter. Newtons per cubic meter. Okay? So dimensional analysis again. For the upper, this one, this is based on P over rho G. P over rho G. P is Newton per meter squared. Rho is kilogram per meter cube. G is meters per second squared. Okay? The upper portion, Newton per meter squared still. Okay? For the lower portion, the meters per second squared and the kilogram, we factor that out. Then we get kilogram times meter per second squared and the 1 over meter cubed from the original density when it is separated from kilogram. So kilogram per meter cube becomes kilogram times 1 over meter cube, and then your meters per second squared. Okay? The kilogram times meter per second squared, this becomes Newton. Okay? And then multiplied by 1 over meter cube, Newton per meter cube. Then you get Newton per meter squared over Newton per meter cube. Okay? And if we divide this, then we get the reciprocal of the denominator, meter cube per Newton. The newtons will cancel, the meter squared will cancel. We will be left with meters. So it checks out that the pressure head has a unit of meters. That's from PV, that started from P times V over mg. Any questions po sa derivation? Okay, next. Velocity head naman, same thing. 1 half mv squared divided by weight or mg. So here, the m, the masses, will cancel out. So we will be left with v squared over 2, 2 from the 1 half times g. V squared over 2g. Unit analysis, v is meters per second, g is meters per second squared. Okay? You will get meter squared per second squared over meter per second squared. The seconds will cancel. One of the meters will cancel. You will get meters also. And lastly, elevation head, mgz divided by weight, mgz over mg. The m and g will cancel out. So you will be just left with z or elevation. Okay? So the total energy head now from the three terms will be P over rho g plus V squared over 2g plus z. Okay, so please be familiar with this one because this is what we will be using most of the time. The energy head, total energy head. Total. So, okay, any questions po? Okay?
Wala.
Yan. So, concepts pa lang naman tayo today. But let me give you an example. For we end, calculate the energy flowing in the pipe. So I have a pipe with an H2O, water. The center of the pipe has an elevation of 2 meters with respect to the ground. Okay, with respect to the ground, it means this is my datum line or reference line. Okay? The pump has a gauge pressure of 5 kilopascals and the fluid has a velocity of 10 meters per second. So what's being asked is to calculate the energy flowing in the pipe, the energy potential or energy content, basically. So given this, so remember pala, the energy, tama ba? Yes, the energy of pressure is based on the pressure difference with respect to the outside or the ambient. Okay, ambient, outside, atmospheric, basically. So what we will be using here for the pressure head, the P, is always the gauge pressure. Because if the pressure of the inside and the outside are the same, then there is no pressure difference. No pressure difference means no pressure energy. Okay, pressure this P in the pressure energy element is gauge pressure always. Okay, pressure difference lagi yan. Okay. So calculate now the total energy. So what we do, we just substitute all the properties of the fluid into our energy equation. Okay, P over rho G, your pre or gauge pressure is 5,000 pascals. Our rho is 1,000 kilogram per meter cubed. Our G is 9.81 meters per second squared. Our V velocity is 10 meters per second squared yan over 2 times 9.81 meters per second squared plus elevation or average elevation, which is 2 meters. So combining these three terms, I will have three values, and for combining three values, I'll get 7.6065 meters. So this is my total head or total energy head for this system. So I can say or I can state that my system has a total energy head of 7.6065 meters. Okay? Again, this is meters, but this is not directly this do not interpret this as elevation. Okay? This is energy head of the system. Okay? Any questions po? So you can review this more over the week. Okay? But tomorrow kasi I would like to discuss sample ba ako? Hindi. Tomorrow kasi let's discuss na the Bernoulli. The Bernoulli fish. Para kasi face-to-face siya. So, it's a little bit difficult. So, bukas natin i-discuss yun para you can ask questions during the face-to-face. Okay, so we will be using this concept tomorrow. I'll give more examples tomorrow. Any questions po? Actually, that's the end na for today's discussion. So tomorrow, to remind you, is our face-to-face class schedule. Face-to-face, yes. It's our first face-to-face after the midterms. So it's week 12 already. Our last face-to-face was week 6, I think. Week 6. So it's more than a month already since we had face-to-face. So take the opportunity tomorrow to ask questions for anything that might confuse you for fluid flow ever since we discussed fluid flow. Okay, and also a reminder, please bring your problem set number 1 tomorrow. Physical copy. I can collect them tomorrow and check them. Okay? Any last call po for final questions? Okay. If no more questions po, then that will be all for today. Thank you for coming in today and see you tomorrow.
Thank you po, sir.
Thank you po,
Thank you
sir.
po.
Thank you po.